did his postdoctoral research in University of Leeds and in University of Georgia, and now he works on that is mainly focuses on the theoretical aspects in several quantum information processing theory field. And today he will talk on 2 applications of quantum walks. Are you? Yeah, I see the screen loaded already. So I welcome Professor Colin Benjamin, and screen is now you can talk, go on with your talk. So would you like to have questions in between, or you would like it to be at the end?
As you feel okay with it.
Okay, that is fine. All right. So should I remind you? So it is around 50 minutes talk and 10-minute interaction would be ideal.
Thank you. Thank you so much.
Okay, please carry on. Please carry on.
So, yeah. So can you all see my screen? And am I audible?
Yes, yes, but this is not full screen. This is not full screen. Yeah.
Oh, I see. So this is not full
So
screen.
you may have to
no idea. Okay.
Start the slideshow.
Yeah, I have started slideshow anyway, but I have no idea why it's not full screen.
Okay, so maybe on the left corner of down.
Let me stop and do it again.
Okay, fine.
Let me do it again. Is it full screen now?
No, it's not.
It's not. I have no idea why it's not full screen, but
so I think
can you...
yeah,
okay,
it should be okay. We can see it.
But
it's not.
You can go to the option from beginning.
Here in the option.
Top left. Below
Top
file.
left.
Below file.
Okay.
No. Go back.
No.
Okay. From beginning.
From beginning.
Okay. Sure. Now is this okay?
No.
No.
Try one thing. Come down your screen to the.
Okay. Do the Control L.
Control L.
No, this is not a PDF. So it is not a PDF.
No, this is a PowerPoint. This is a PowerPoint.
So down you have notes and some symbols down there. You may that is in the slide down.
That's right. It's notes. Yeah.
So in that you'll see a full screen, not notes. In one of these you will find
this one.
Then you click on it.
Is it this one?
You will see a full screen option in one of those 4 symbols. Notes and next one. You have to see where do you see the full
slide
screen.
sorter, normal, reading view, slideshow, zoom.
No, not that.
Then fit
not
slide.
that. Okay,
not that one.
I think it's
this
better
for
you continue with this. It's okay.
It's okay. Okay.
Yeah, fine. Thank you.
I have got a chat message. Please click on the cup at the right bottom. Okay. So there is a cup here. Someone is telling me to click on that. Let me just try it for once. Does it work?
No.
Okay. Fine. So it's not working anyway. So let's start with whatever we have. So first of all, I would like to thank Professor Panigrahi for organizing this online meeting regularly for the past 3 years now. And he has been kind enough to invite me, and I've got a great opportunity to share some of the current works I have been involved in. So in this talk, I will go over 2 of my recent works. One is on generating maximally entangled single particle states using discrete time quantum walks. And another is on improving the Google PageRank algorithm via quantum stochastic walk. So these two are quite different fields. The thread which joins them is quantum walk, and they are currently under review, both of them. And they have been published with two of my students, Dinesh Panda, who is a PhD student, and Nani Dudhe, who was a master student working with me last year. Okay. So what are quantum walks? Basically, we know classical random walks, right? You toss a coin on a 1D line and you move either to the left or to the right. So here if it's heads, you move to the left, and if it's tail, you move to the right. So you start at some position, say 0, and then you toss at each time step 1, 2, 3, 4, 5, and then you find out the probabilities. Where are you? And you will see that generally the probability of where you started from is the highest, and then it decreases towards the edges. Now, the same thing you can model using quantum mechanics. So this is a discrete time quantum walk on a 1D line. You replace the coin with now a unitary operator. Here we have taken a Hadamard, and then moving to the left and right depends upon the outcome of your coin operation, and that is defined by the shift operator. And the first sketch here represents the coin position. Let's say you are in the coin state 0, and the position in the 1D line. Let's say you start at the 0 in the 1D line. And when you do it regularly at each time step, you will find a probability distribution table as follows. And you will see after the time step 2, there is a marked difference between the quantum walk and the classical random walk. So much so that at time step 5, you have a higher probability of being closer to one of the edges than to the center from where you started from. And that is what distinguishes a quantum walk or a discrete time quantum walk from a classical random walk. So what are the main differences between a classical random walk and a quantum walk? So here we have done the probability distribution at 100 time steps, and you can see a neat Gaussian probability distribution with a standard deviation which goes as square root of the number of time steps. Now the same thing if I plot for say 100 time steps, I will find a probability distribution which is completely different from the classical one. It is not Gaussian, it is asymmetric, and the probability to find the walker further away from the origin is maximum actually. And the standard deviation here is not square root t, but is t. So quantum walk spreads much faster. It is ballistic propagation compared to classical random walk, which is diffusive propagation. Okay. Now, if I change my initial coin state from a 0 to a superposition, I'll get a symmetric quantum walk probability distribution. But again, the standard deviation would go as t. I can also remove the coin completely and look at a continuous time quantum walk. There is in discrete time quantum walks, we have to have a coin and a shift. Here in continuous time quantum walk, we do not need a coin. And the advantage is you can apply it to any graph of any arbitrary degree. So there in discrete time quantum walk, generally to 1D and 2D lattices you can apply, which is much more structured. But in continuous time quantum walk, we can apply it to any graph of any arbitrary degree. And the advantage is because there is, if you want to implement a discrete time quantum walk on an arbitrary graph, for each vertex, it may be connected to many other vertices. In that case, you have to design a coin for each vertex, and that becomes too difficult. So here what you do is you evolve the whole Hamiltonian, or basically the adjacency matrix, which is written here, of the graph. And of course, it is independent of time. So you evolve it in time, and this is the unitary operator corresponding to that. You start at some position on your graph, and as you evolve it in time, you go to some other position in the graph. And you can, for this 1D line, you can discretize your matrix as such. It's basically a tridiagonal matrix. And then you can calculate the probability, and it turns out that the probability of finding yourself at some position n at finite time step t is given by this Bessel function. And when you plot it for this value of gamma, this coupling parameter, you'll find that it almost reproduces the symmetric discrete time quantum walk. And again, in this continuous time quantum walk, we have the standard deviation is proportional to T. So what is the main, so what are some applications of quantum walks? So applications of quantum walks are basically in universal quantum computation, where we have where people have implemented quantum gates via scattering, then applied discrete time quantum walks to quantum search algorithms, where we have seen the application of Grover's search algorithms, and we have implemented Grover's search algorithms in via quantum walks and seen the advantage of that. On page rank algorithm, which I will discuss in today's talk, then simulating other physical systems via quantum walks. For example, you can simulate the Dirac equation, simulate topological phases. So it's really advantageous using quantum walks. Then single particle entanglement, which I will in this talk discuss. Then transport. People have speculated that there is some quantum interference happening in energy transfer in photosynthesis, given its almost 10% efficiency. So we have also worked on that. That was published some time back, but in today's talk, I will not discuss that. And then, of course, they have been experimentally realized in many photonic and optical systems, cold atoms, trapped ions, bosons and condensate, and many other things. Okay. And my collaborators in this talk are one is my student Dinesh Panda, with whom I worked on single particle entanglement, and this is Nani, with whom I worked on the page rank algorithm. So first, we'll come to the single particle entanglement. Here, what we mean by single particle entanglement is that we intend to entangle different degrees of freedom of the same particle, say the polarization and the spatial mode of a photon, or the spin and position of an electron. It was first experimentally realized by Weinland in 1996. He, of course, is the Nobel laureate, and he realized it with cold trapped single beryllium ions, and by applying laser pulses. So these are laser cooled single beryllium ions trapped in a harmonic potential, and they were able to see entanglement between the local spatial position of the coherent wave packet and the ionic internal electronic state. And here is a cartoon of that scheme. So here is the ionic electronic state. These are the internal degrees of freedom of the beryllium ion. And this is the coherent atomic wave packet localized either at this spatial position X minus or X plus. And they could see this entanglement between the different degrees of freedom of this beryllium ion. Okay, and this was reported here in Science. Now, what are the advantages of single particle entanglement? First, it encodes more information at a single particle level. And there is something called quantum joining here, in which qubits encoded via two distinct qubits can be combined to a single photon-based qubit. And of course, they are much more robust because it is single particle, non-locality is not there. Therefore, they are much more impervious to the deleterious effects of decoherence and dephasing. And then single particle entanglement has applications in analyzing states of photons and elementary particles, as well as in engineering photonic gates and other devices. There's a nice review by Azin, where you can read much more about the advantages of single particle entanglement over two particle or interparticle entanglement. Okay, so what is the motivation? Several manuscripts in the past 2-3 years have reported on how to generate single particle entanglement via quantum walks. So one of the first was by these authors in this paper, and they took an arbitrary distribution of, say, initial states, and then they plotted they had a discrete time quantum walk, and then they over a one-day line, and then they plotted the Schmidt norm. The Schmidt norm, the maximal Schmidt norm is square root 2. So they plotted it versus the number of time steps for different coins. So for a Hadamard coin, for a random coin, and then for some optimal coin distribution where they optimize over all coin parameters. Now this scheme gives recurrent entanglement for time-step steps. Now the reason we give plots till time-step steps, because in experimentally implementing discrete time quantum walks on 1D line, people have not been able to experimentally see it beyond, say, around 10 or 20 time steps till now. So going over 20 time steps, therefore, is till now experimental capabilities haven't been that developed. So here the problem with this scheme is there is an optimization problem. So effectively you are having n number of coins, which is very difficult to manage experimentally. But the advantage is that you get maximally entangled. So it reaches maximal entanglement at a few places before time step 10. A very recent work by these authors also predicts maximal entanglement, if you see the picture here, but with, again, 2 coins. So they have reduced it from multiple coins, n coins at each time step a different coin, to only 2 coins, the Hadamard and the identity, and they've implemented it over a single line. And they claim that there is maximally entangled single particle states they obtain beyond the 3rd step. And this is a very good proposal, but of course, there are still 2 coins. We also have worked in this in a previous work by Parando sequences, where you alternate between 2 different sequences, either with only Hadamard or with the Fourier coin, or the Hadamard or the NOT operator, or similarly the miracle coin or the Fourier coin, by using these 2 losing games can lead you to, by combining 2 losing games, which is the Parando paradox, you get a winning outcome. So with that idea, we formulated this work, and we saw that indeed with 2 coins, either Hadamard or Fourier, we can get maximally entangled single particle states within 10 time steps. So the main motivation of our work with Dinesh was, can we have a single coin implementation instead of having 2 coins or a coin with identity? Can we have effectively only a single coin implementation of maximally entangled single particle states? So for that, we choose cyclic graphs. Here we have some cyclic graphs. This is a 4-site cyclic graph. This is an 8-site, and this is a 3-site and a 5-site. We take completely general coin operators, and obviously, when you have a shift operator on a cyclic graph, you have to have a modular so that would go back in a cycle. And then obviously, we, similarly to a discrete time quantum walk on a line, we have this evolution operator, the shift into the coin. And you start with completely arbitrary initial state with the theta parameter ranging from 0 to 2 pi and phi ranging from 0 to 2 pi. And then after these operations at each site, here k represents the site of the graph. So for a 4 cycle, this k would be 4. For a finite number of time steps, you then calculate the final state and then calculate the entanglement by writing the density matrix, then take the partial trace over the, say, the position degree of freedom, and then diagonalize that reduced density matrix to get the eigenvalues, and either using the Schmidt norm or the von Neumann entropy, you can calculate the entanglement. And obviously, if you are calculating using von Neumann entropy, the maximal entanglement would be 1. And of course, because these are periodic lattices of the cyclic graph, for certain coins, you may end up where you started from. So then it would be what is called an order of periodic quantum walk. And that we can use to our advantage when designing, in generating maximal entangled single particle states. So for n time steps, if I reach the final state, and if I want it to be ordered, then obviously the initial state, I will again get back my initial state after, say, if my discrete time quantum walk has a period n, I will get back the initial state. So the condition for periodicity would be this unitary operator would be identity with a dimension of 2 into k, 2 because we have the 2 degrees of freedom for the coin and k for the K-site cyclic graph. So what we want, our main aim is to have maximally entangled single particle states which are recurrent. Many maximally entangled time steps we should get at time steps below 10 on many occasions. So we have a single coin, and we show that indeed with a single coin you can get a completely general single coin subject to certain constraints. Here phi is the initial state of the single coin, and gamma is a coin parameter. And we see that for this arbitrary coin and this arbitrary initial state, you can get a maximally entangled single particle state at time step 1 for any K-cycle graph. And the initial state of the coin is separable. There is no entanglement at t equal to 0. A subset of this general coin with these parameters and subject to this constraint here is recurrent or periodic maximally entangled single particle states on both 4-cycle and 8-cycle graphs. And the proof of this is very simple. You equate the Schmidt norm of the entanglement entropy at time step 1 to 1 and solve it to get the exact coin parameters which give MESPS, and then check whether these coin parameters satisfy the periodicity condition here. If they indeed satisfy, then you will get a periodic or recurrent maximally entangled single particle state. Okay. So we indeed saw using these arbitrary coins here and here this R coin, which is this coin parameter, and this Q coin, this, and again this C4, this arbitrary coin, we indeed see maximal and entangled single particle states at many places before the 10th time step. This is the time step 10, and we see 1, 2, 3, 4, or 5 occasions where you get maximally entangled single particle states. Of course, we average over all beta values. Beta is the, if you remember, the initial coin state. So we also have seen not only, and these are for Hadamard coins also, we get maximally entangled single particle state before the 10th steps, before the time step 10 on many occasions for each of these coins, either Hadamard or any arbitrary cycle coin C4. We also note that using 2 coins and effective single coin, that is coin and identity, you can generate these recurrent maximally entangled single particle states on both odd, that is 3, 5 site, or even 4, 8, 6 cyclic graphs. Okay. Now, how do we experimentally realize this single particle entanglement with quantum walks? One way is to use photons. You encode the quantum walk point state in the photonic polarization degree of freedom, whether it's the horizontal or vertical degree of freedom. The Walker position state you encode in the photon's spatial degree of freedom. And then for the coin operation, you use halfway plates. A halfway plate set at, say, some 22.5 degree will correspond to a Hadamard. A quarter wave plate at 45 degree corresponds to a Fourier coin. Absence of a wave plate will be an identity. And then for the shift operation, you can use a calcite beam displacer, and you can implement a shift like that. And then to evaluate the Schmidt norm or the entanglement entropy, you use some post-processing measurements like average polarization, and then you get your Schmidt norm. So these are 2 papers which have calculated experimentally the single particle entanglement in this paper, and also in a cyclic graph. People have not calculated entanglement, but have calculated, measured the probability distribution and implemented a quantum walk, a discrete time quantum walk using photons on a cyclic graph. So this scheme of ours, which generates maximally entangled single particle states on a cyclic graph, is very much experimentally implementable with the most lowest resource required. We don't require 2 coins, we don't require multiple coins, we don't require optimization, we just require a single coin. We have given an application of maximally entangled single particle states related to encryption decryption protocol in our paper, but it is no means the only application. Wherever you have interparticle entanglement, apart from that non-locality thing, it makes a, if it doesn't make any difference, then these MESPS states are as good as any non-local maximally entangled state, since they violate both the realistic and non-contextual hidden variable theory tests like the Bell inequalities, and so they can be used in any scheme which uses entanglement. So the best thing about these generating these kind of entangled state is that they are robust to decoherence, plus they are very cost effective to prepare. So in this cryptographic protocol, we use the single coin say evolution sequence of Hadamard coins on a 4-cycle graph. Say Alice wants to send any of her messages encoded in the site basis of our 4-cycle graph, either 0, 1, 2, 3 to Bob. So first Bob generates a public key using the coin and the coin state and the position states, and applies a Hadamard, say 5 times, to generate a maximally entangled state. So your public key is a maximally entangled state. Then Bob, after generating this maximally entangled state, which acts as the public key, sends it to Alice. Alice now encrypts the message by encoding a shift operation. So depending upon what kind of shift she wants, what kind of message she wants to send, she does the shift. And then Bob decrypts the message by applying again the Hadamard coin 3 times. And the catch here is that the Hadamard coin applied 8 times goes back to the initial state. So this on a 4-cycle graph, Hadamard coin gives a periodicity 8 probability distribution. So you go back to where you came from, and therefore Bob then can do a mod operation and securely obtain Alice's message. So to summarize the first part of the talk, so our work is a state of art in the field of controlled entanglement generation. We report for the first time only a single coin can generate maximally entangled single particle states. Of course, we also show how to generate MESPS using effective single coin and also 2 coin. And the single coin is very easy to implement experimentally. It is resource saving. It requires very less resource. And it can generate entanglement at both small within 10 time step as well as large time steps. And of course, we report effective single coin and 2 coin evolutions. Okay, so that ends the first part of my talk. I would like to know if there are some questions. We can take them on the first part of the talk before I move on to the second part.
Any questions from the audience on single particle entanglement? I think
if there are no questions, then okay, so fine. So we move to the second part of my talk, which is on quantum page rank, and the outline is as follows. First, I will describe what is classical page rank. I will then move on to quantum page rank, which is implemented using a quantum stochastic walk, and we will analyze many different kinds of networks which can mimic the World Wide Web. And you can find more details in this paper. So what is the PageRank algorithm? So the PageRank algorithm, as designed by Sergey Brin and Larry Page, it ranks web pages according to the nature of the search and put forth the most relevant web pages towards the top. Now, the key to a PageRank algorithm is the number of links determines the importance of a website. The quality of links also matters, among other factors. And even if a website has fewer links than others, but if the links are from well-known websites, which are called hubs in World Wide Web, then it is likely to receive a higher rank. And this PageRank algorithm, of course, is the backbone of Google search. You can read more about it in this Wikipedia article. So what are the basis of this PageRank algorithm? To rank the web pages. So what does the classical PageRank algorithm do? So it must distinguish between the importance of websites. So it must degeneracy between websites. So if there are degeneracies, each website gets the same rank, then it's very difficult for any user to find out which one is better to go to. So as far as it's the goal of any PageRank algorithm would be to reduce any degeneracy in its ranking. Now the Google PageRank OVX degeneracy in ranks, and second, it has a very fast convergence time. So how does it do it? So if you remember when internet first came, it was the pre-Google age. I think it was 99, 2000, and I was just a beginning PhD student. We had search engines like Netscape and Lycos, LookSmart, etc. So what they used to do when you put a search query, then a whole host of websites with just matching content in no particular order would come up. And it would be very difficult to go through this maze of different websites. And the user then looked through the whole list and found what was meaningful, and she or he has to scroll down sequentially through all the matches. Now, Google's master stroke was in adding a second step, which was to rank these websites with the matching content based on links. So first you get a search list in no order, and then you find the links between these such that you can rank. So higher those websites which have more links between them will get a higher rank than those which have less number of links. So based on these links, you get a second step, and by this you get a much better search. And of course, by 2003, when Google first entered, instead of search, we just say Google it. It was so good and it was so effective. So what is the basis of this classical PageRank? This classical PageRank acts according to a classical continuous time random walk. So you can model any complex network. So this is just a description of classical continuous time random walk, not of classical PageRank. So any complex network can be modeled as a graph of, say, m vertices with e edges. And if you want to model a network of different websites, such as the World Wide Web, your vertices would represent the web pages, and the edges would represent links from one web page to another. You can formulate an adjacency matrix. It will have a entry 1 if edge is directed from J to I, and if it is undirected, then you will get both the reverse and Aij to be 1. Now, the out degree of a vertex is a very relevant notion here. It defines the total number of edges leaving the vertex. To evaluate the continuous time random walk, you have to first start from some place. So you initialize your probability vector from some vertex of a graph, and then you evolve it in time. You evolve it in time via the transition matrix, and this transition matrix is just your evolution of this adjacency matrix or the generator matrix H in time. Yeah. And as you go iterate this equation over and over again, you go over to a stationary state where further iterations don't change the probability distribution. So this equilibrium probability distribution gives the entries of the stationary solution, and this will present the ranks of the different vertices. So this is behind the classical PageRank algorithm. Now, there is the problem here, because when you model any adjacency matrix as a World Wide Web, in the World Wide Web, you may have web pages which have no links to any other web page. If your search ends at such kind of a dead end, then obviously your search will end there. So to avoid such dead ends, what you do is you transform your adjacency matrix to what is called the Google matrix by putting a factor of 1 by n, so that if you end up at some directed web page which doesn't have any links to any other web page, then there is a finite probability of 1 by n to jump to any, again, start your search at any other random web page. So this is a certain modification of your adjacency matrix you have to do. Now we come to quantum PageRank. Now in quantum PageRank, what we do, I described to you the continuous time quantum walk. We modify the continuous time quantum walk via this Lindblad master equation to incorporate the effects of the environment. So if you look at the first part, it is basically the continuous time quantum walk at omega equals to 0. Omega is the parameter which interpolates between the continuous time random walk and the continuous time quantum walk. Basically, this is the same thing what we saw in the continuous time random walk, but now we will use this Kosowski-Lindblad mastery equation to evolve our adjacency matrices in time. So OX here is the Lindblad operator. These are sparse n cross n matrices. As I said, the first term here represents a contribution from coherent dynamics, while the second term represents a contribution from incoherent dynamics. We use two methods of quantum stochastic walk analysis, what is called only incoherence and dephasing with incoherence. What are these? So in only incoherence, we take this Lindblad operators to be only off-diagonal matrix elements, while in the dephasing and incoherence model, we take the Lindblad operator to be the Google matrix elements. So all terms, we don't distinguish between off-diagonal and diagonal, we take all the terms of the Google matrix. And then we evolve it in time. So how do we evolve it? We first vectorize the density matrix and then evolve it in time. We first start from some random web page, and then as we evolve this O matrix in time, we reach the equilibrium. So either using this only incoherence or dephasing with incoherence, which distinguishes these OX or Lindblad operators, and using different values of omega, we can play around and find out where we reach the equilibrium. Now, there are two parameters which determine how good your search is. One is degeneracy, the calculation of degeneracy, and the other is convergence time. Now, any PageRank algorithm, whether it's classical or quantum, will have some degeneracy. How better we can resolve this degeneracy is what distinguishes one algorithm from the other. So any vertex with more links, as I said, will have a higher rank, and any vertex having links from a higher rank vertex will in itself have a higher rank. Now, as I said, because some vertices have the possibility of getting the same rank, as they might have same number of links from other websites, therefore we will get degeneracy. So we'll first check using classical PageRank and then compare it with the quantum PageRank with the two quantum stochastic walk schemes, how better our methods can resolve this degeneracy. And the second parameter which to evaluate any search algorithm is this PageRank algorithm is to find out how quickly it goes over and gives us the result. So if we calculate the norm, which is the difference between the density matrix elements at time t to the equilibrium or the stationary state. So if we put some small value of epsilon, then the time it takes for us to reach the equilibrium state defines the convergence time. So the less the convergence time, the better the PageRank algorithm. We chose 4 different kinds of networks to base our study on. We chose the scale-free network, the Watt-Strogas network, the Erdos-Renyi network, and the spatial network. All of them have some property of small world networks. The Erdos-Renyi, Watt-Strogas, and scale-free networks differ based on this probability distribution. For example, the scale-free networks, the vertex degree follows this power law, where D is the degree and H ranges from 2 to 3. So basically, a few degrees have a high probability of having lots of edges, and lots of other vertices have very small number of edges. So this is one example of a scale-free network is the Barabasi-Albert graph, and the other is the price graph. Similarly, any of these networks can be a proxy for internet networks, such as the World Wide Web, but they differ in certain small degrees. All of them, as I said, have small world networks. So what is a small world network? Any two nodes, that means any two web pages or any two vertices of your adjacency matrix will have a relatively small distance between them. And then the clustering is high and hubs are present. So hubs in website, in web page terminology would mean such websites like Yahoo and Google, which to which everyone goes to check their email or something like that, or some media website like New York Times or something like that. times of India. So hubs are vertices possessing a large degree, and in turn, the degree distribution will have a long tail. And also, what does clustering mean? If you assume one node is connected to two other nodes B and C, then the chances for B and C to be joined by the edge are high. That is, A, B, and C are all mutually connected, so they form a cluster. And any example of smaller networks could be road maps, electrical power grids, social networks, neural networks, and the internet. Okay, so here we first start with the ADOS-Rennie network, and you can see this is a particular network, and you can see the comparison here which I have given. There is no animation here. Let me just do the animation. Sorry. Where was I? Okay. Okay. So here we have the page rank versus the vertices for the two methods: quantum page rank with only incoherence and quantum page rank with dephasing and incoherence. And you can see the page rank and the weights do not differ that much from the classical page rank to the quantum page rank. Sorry?
3,000 rupees. Halu, musru, vegetables, fruits.
Hello.
Hearing.
I think
Bala
somebody
costly
is
ನೀನು.
talking.
Hearing.
I request.
Bala costly.
ಲೆಕ್ಕ ಹಾಕು ನಾನು ₹1 ಆ ಕಡೆ ಕೊಡವ.
Correct.
Okay, so
Organizers, please mute others and make sure that others are muted unnecessarily.
Yeah, we have muted. Please continue.
Okay. So here is the page rank versus the vertices for the Zachary Karate Club, and here we have another ADOS-Rennie network called the Bernoulli graph distribution, and you can see the page rank versus vertices here also. There is some difference between the weights of the page rank for particular vertices within these blue ticks versus the orange lines for the classical page rank. So when we analyze them, for the number of degeneracies, we see that between classical page rank and quantum page rank, there is hardly any difference as far as the Bernoulli graph goes, and also for the Zachary Karate Club. In the classical page rank, there are 7 vertices which are degenerate. That is, they get the same rank, and therefore they are difficult to distinguish. And the same thing in quantum page rank. So as far as ADOS-Rennie network goes, a lot of a difference. Similarly, for convergence time, if you see, this is the ratio of the quantum page rank convergence time to the classical page rank. So it's almost always for any value of omega. Omega, if you remember, is the factor which determines whether you are in the quantum continuous time quantum Mach regime or in the classical random Mach regime. So omega equals to 0 is the fully continuous time quantum Mach, and omega equals to 1 is classical random Mach. So any arbitrary value of omega between these two extremes means it is a continuous time quantum Mach with some classical features. And you see in this scheme, for any, regardless of omega, the quantum page rank is always takes a higher time to converge to the stationary state than the classical page rank. And in both cases, in the Bernoulli case, there is for a large omega, the quantum page rank is slightly better, but that doesn't make much of a difference. So for ADOS-Rennie, there is hardly much of a difference between the quantum page rank and the classical page rank algorithm. Now let's go to the second one, the Watt-Strogas network. Here we see a real difference. This is the Watt-Strogas network of 100 vertices. And if you see the plot of page rank versus vertices and analyze them through this table, you see, and we generated 5 distinct networks. In all, we saw the classical page rank, the number of degeneracies is 6, 8, 10. But the number of degeneracies in that network for quantum page rank, either through this or that dephasing with incoherence method, are markedly reduced. So here there are just 4 degeneracies. Here in comparison to 6, there are no degeneracies at all. And more importantly, when we look at the convergence time for a large range of omega values, we find quantum page rank beats classical page rank by a factor of almost half. So it's doubly faster for a quantum page rank than for a classical page rank. So in Watt-Strogatz network, if the World Wide Web is a Watt-Strogatz network, then obviously implementing quantum page rank is advantageous. Then there are scale-free networks. Here too, you can see the degeneracies. Here it's almost double-digit degeneracy throughout, almost 78 degeneracies, and this is over 100 vertices. So over 100 vertices with the 78 degeneracies, that means classical page rank effectively fails here. But if you compare with quantum page rank, here also there are almost for all this Barabasi-Albert graph distribution, we only get single degeneracy, only single digit degeneracies here. And but the convergence time is not much better than classical page rank. To go to spatial networks, there too we find slight betterment for quantum page rank as compared to classical page rank, but for the convergence time,
sorry, we see your slide 28, so we do not see. So are you talking?
What?
We see slide number 28.
Oh, I see. You're still stuck in slide 28. Okay, okay. Okay, so I moved to, okay, from Erdos-Renyi, I have moved to Watt-Strogatz. Okay, did no one see this?
We see
we are
29.
able Okay, okay, sorry about that. This is something wrong. So let me go over the Watt-Strogatz again. So you see here the Watt-Strogatz network, and when you implement a classical page rank on this Watt-Strogatz network, we see that the quantum page rank resolves these degeneracies much better than the classical page rank. So in the classical page rank, we have 6, 8, 10, 8, 9, while in the quantum page rank, we have just single digit degeneracy. So it resolves degeneracies better, and as far as convergence time goes, it's almost double faster, doubly faster than the classical page rank. Now going to scale-free networks, again we see the degeneracies in classical page rank are huge for the scale-free network. It's always in double digits, but when you come to quantum page rank, it's single digits. But the convergence time is slower. It's always slower throughout the range of omega values, but when omega is very high, it slightly dips. Okay. And then for spatial networks, here the convergence time is slightly better, and the degeneracy resolving capacity of quantum page rank is of course better. So in two cases, spatial networks and Watt-Strogatz network, we see a definite improvement for quantum page rank as regards convergence time as well as degeneracies as compared to classical page rank. But for the Erdos-Renyi networks, we see no improvement, and neither for the scale-free networks. So to summarize part 2, our aim in this work was to check whether quantum page rank can resolve degeneracies which are unresolvable by classical page rank, and the convergence time, how much time it requires to reach the stationary state. We use the methods, the quantum stochastic walk with only incoherence or dephasing with incoherence, and the results, the efficacy of both of resolving degeneracies is in general same or higher than classical page rank, and the convergence time either marginally differing or significantly better, especially for the Watt-Strogatz network. Here we have given a comparative chart for each case. So in Watt-Strogatz, there is an improvement in both degeneracy resolution and convergence time for quantum page rank as regards classical page rank. But for ER networks, there is not much difference. Scale-free also, there is not much difference. And for spatial networks, there is some slight difference. Okay. So with this, I would like to end my contribution here. Thank you so much for this opportunity again. And you can find a list of my publications and other things here in this my webpage. Thank you.
Thank you. Let's thank the speaker for some new thoughts on these things, that is random walks and its extensions. So if there are any questions, please unmute yourself and ask your questions.
I have questions.
Please
Sure,
go ahead.
please.
Yeah, thank you for your talk. Could you please show the form of Hamiltonians used by you in the first part and the second part of your calculations? Because I suppose you are using Lindblad equation, right?
No, the second part only we have a adjacency matrix which builds on the continuous time quantum walk and uses environment. So we have a Hamiltonian, which is basically the graph adjacency matrix, you can say. In the first part of my talk, I was talking about generating single particle entanglement, and there you don't need any Hamiltonian. It's a discrete time quantum walk on a 1D line. Or in our case, in our paper, we have a cyclic graph. So there is no Hamiltonian as such. It's just a graph on which you apply a coin and a shift, just similar to what you do in a classical random walk, but now with a quantum state.
Mm-hmm. Okay. Second question is how you will identify which vector you need to take if two eigenvalues have the same value. I mean,
okay, so this is regarding, okay, I got a question. So this is regarding the second part of my talk.
Yes.
And the question is, where do you start your search from? So you can start your search from whether it's in this classical continuous time random walk or the quantum stochastic walk. As I said, the Google PageRank is a two-step process. First, based on your search query, a whole list of matching websites in no particular order are formed. So that is where you start your search from. So in that no particular order, you first go to any arbitrary. You can start your search from any arbitrary web page. Okay. So any arbitrary web page you start your search from, and then because it determines how linked this website is to the other links, you will find that when you iterate it significant number of times, you will reach the state where all web pages or all vertices which have higher number of links compared to others will be ranked higher. That means the weight in this probability vector of those websites would be higher than those who have lower links to others. So you can start at any arbitrary place and you iterate it in time, and you will find your search outcome, which is higher. The websites with higher number of links to each other will be ranked higher than the rest.
So I assume that this degeneracy comes from the open systems, right?
No, degeneracy will occur because the number of links between web pages may be same. If the number of links between web pages is same, classical PageRank effectively fails. So let's say you have a web page you have constructed which links to your academic institute, and then you will have just a single link. Another faculty with same interest as yours will also link to the same EA, and both will have same number of links. So in that respect, it is very difficult to distinguish between these two web pages. So that, and therefore they would be ranked at the same level with the same rank.
Okay. Any other questions? So I wanted a very primitive question. This is about what you have taken is the master equation, Lindblad equation, generally for this evolution in the second part. So I wondered
Mm.
if it happens to be a non-Markovian kind of evolution, you don't have any way to proceed further. Do you
Yes.
have you thought about it?
Well, no. We haven't thought about it because we built our the quantum page rank is built from the classical continuous
Yeah.
time random walk, which has a Markovian, as you see. So
Yeah.
if we go beyond that, then yeah, we don't know what we'll get. But yeah, we haven't thought.
Even
about
in classical case, you do
Hmm.
have non-Markovian processes. Stochastic
it.
processes are there.
Yeah.
I don't know if they have tried it for page rank issues. In classical,
Oh,
stochastic.
that's a good question. I also
Okay.
don't have much information on that.
All right.
No,
Anyway,
that's a good question. Thanks.
thank you for this wonderful exposure. This is something
Mm.
new to many students here and also experts. Thank you very much for your talk.
Thank you. Thank you so much.
All right. So now we move on to the last talk of this session. So is Manabendra there? He had done his PhD. I know it was experimental work, but I'm not